Welcome to Chapter 11, Public Key Infrastructure and Encryption. Let's look into this lecture together. This is your Professor T. Freed Muhammad. We will look into implementing PKI and encryption solution to ensure the confidentiality of the business communications. The key concepts we will discuss in this lecture are PKI components or public key infrastructure components and their roles, non-repudiation and digital signature, PKI certificate authorities, so CAs, and encryption processes. The PKI or public key infrastructure that provides a secure mechanism for business and e-commerce transactions, a community of trust and infrastructure to make the internet safer, a level of security needed for multi-layer security system, a framework that consists of programs, procedures, and security policies, employs public key cryptography and X.549 standard digital certificates for secure communications. PKI is a hybrid system for symmetric and asymmetric key algorithms. Now let's look into all these with one example each. The PKI is like a secure system that helps manage digital keys and certificates, which are essential for keeping online communication safe. Think of it like a university management system that ensures only authorized people can access certain information or perform specific actions. In this system, the certificate authority plays a crucial role similar to the university's registrar's office, just as the registrar's office verifies the issues official documents like transcripts or diplomas. The CA verifies and issues digital certificates. These certificates confirm the identity of users, devices, or services within the university's network. For example, when a student wants to access their grades online, the CA ensures that the students is who they claim to be, preventing unauthorized access. Now imagine a professor wants to send a confidential email to a colleague about research project. The PKI system, with the help of CA, ensures that the email is encrypted and can only be read by the intended recipient. The CA issues digital certificates to both the professor and the colleague, which contain their public keys. These keys are used to encrypt and decrypt the email, making sure that even if someone intercepts the message, they won't be able to read it without the proper certificate and private key. This way, PKI and the CA work together to maintain the security and privacy of communications within the university management system. Next, we look into the registration authority. In the context of university management system, the registration authority acts like the admissions office. Just as the admissions office handles student enrollments and verifies their identities before they can access university services, and the RA manages the initial registration process for users or devices, and within the PKI system, when a new student or faculty member joins the university, the RA or registration authority ensures that their identity is properly verified before issuing them the digital certificate. PKI is like a digital security system, as we discussed earlier, that helps keep information safe and secure when it is sent over the internet. Imagine you are sending a secret message to a friend and you want to make sure that your friend can read it. PKI uses special keys like passwords to encrypt or scramble the message so that even if someone else sees it, they can't understand it. These keys come in pairs, public key, and anyone can use the encrypt message. In a university system, PKI certificate repository is like a secure vault where these keys are stored and managed. When the students or staff need to send sensitive information like grades or personal data, the system uses the repository to find the right keys to encrypt the data. certificate validation happens in a similar phase, and key recovery service absolutely goes and figures out in the repository what were the keys, and the time server allows to manage the entry and exit time of using any services. The signing server allows us to look into making sure that the signing is happening by a certified authority, to make sure that you are getting the digital timestamp for the use of service applications. Encryption and cryptography is the process of applying an algorithm to clear text or plain text data resulting in ciphertext. The crypto system is a hardware or software system that provides encryption and decryption made up of the encryption algorithm, keys, software, and protocols. The secret piece of the crypto system is the key in reality that we work with. Now let's look into the encryption and cryptography in this pictorial representation, how the encryption process works with a university system as our main example. This image illustrates the process of encryption and decryption, which is crucial for securing digital communications within a university system. In this process, the sender starts with the clear text, which is the original readable message or data. This clear text is then encrypted using an encryption key, transforming it into ciphertext, a scrambled, unreadable format. This encryption ensures that even if the data is intercepted, it cannot be understood by unauthorized individuals. In a university setting, this could involve encrypting sensitive information like student grades, research data, or personal details before sending them over networks. On the recipient's end, the ciphertext is received and then decrypted using a decryption key, converting it back into clear text. The decryption process is a reverse of encryption and is essential for accessing the original information. The use of keys in this process highlights the importance of key management in the university's IT infrastructure. By securely managing and storing these keys, the university can ensure that only authorized personnel can decrypt and access sensitive data, thereby maintaining the confidentiality and integrity of the information across the institution. So symmetric algorithms use shared secret keys for encrypting and decrypting the data. Symmetric encryption systems allow only the users who have the secret key to read the data, as mentioned earlier. Symmetric key systems encrypt and decrypt information more quickly than an asymmetric system. Symmetric key systems require a secure method to create and exchange the secret key. Each pair of users require a secure method to create and exchange the secret key, making key management difficult as the number of pairs of users increase. Now let's look into this with another example. The image depicts the process of symmetric key encryption, which is the method used to secure data in a university system. In this process, the sender starts with clear text, which is the original readable message or data. This clear text is then encrypted using a shared secret key, transforming it into ciphertext, a scrambled, unreadable format. The encryption ensures that the data remains confidential and can only be accessed by those who possess the secret key. In a university context, this might involve encrypting sensitive information such as student records, financial data, or research findings before transmitting over networks. On the recipient's end, the ciphertext is received and then decrypted using the same shared secret key, converting it back to the clear text. This decryption process allows the recipient to access the original information. The use of shared secret key in symmetric encryption highlights the importance of securely managing and distributing this key. In a university setting, this means ensuring that the only authorized individual have access to the key, thereby protecting the confidentiality and integrity of the data. This method is efficient and secure provided that the secret key remains confidential and is only shared by the trusted parties. Asymmetric algorithms use pairs of related keys, public and private, for encryption and decryption. Public key can be known by anyone. Public and private keys are related, and anything encrypted with one can only be decrypted with the other. Now let's look into this in a little bit more depth. This image illustrates the process of asymmetric key encryption, a crucial method for securing communication within a university system, as we are taking that our main example. In this process, the sender starts with clear text, which is the original readable message or data. The clear text is then encrypted using the recipient's public key, transforming it into ciphertext, a scrambled, unreadable format. The use of recipient's public key ensures that only intended recipient who possesses the corresponding private key can decrypt and read the message. This method is particularly useful in university setting for protecting sensitive information, such as student grades, personal details, or confidential research data. On the recipient's end, the ciphertext is received and then decrypted using the recipient's private key, converting it back into clear text. This decryption process ensures that the only intended recipient can access the original information, maintaining confidentiality. Asymmetric encryption is advantageous because it eliminates the need of shared secret key, making key distribution simpler and more secure. In the university context, as we are discussing as main example, this means that individuals can freely share their public keys without compromising security, while keeping their private keys secure to protect their data. This approach enhances the overall security of digital communication within the institution. So now you're looking at the similar sender private key and the sender public key. Let's look into this with an example. This diagram demonstrates another example of asymmetric key encryption, which is essential for ensuring secure and authenticated communication within the university system. In this scenario, the sender starts with clear text, the original readable message or data, and encrypts it using their private key. This process transforms the clear text into ciphertext, a scrambled and unreadable format. By using the sender's private key for encryption, the recipient can be assured that message truly originates from the sender, providing a layer of authentication. This is particularly important in a university setting for verifying the authenticity of communications, such as official announcements or directives from faculty. On the recipient's end, the ciphertext is received and decrypted using the sender's public key, converting it back into clear text. This decryption process allows the recipient to read the original message while also verifying its source. The use of the sender's public key ensures that the message has not been tampered with during the transmission phase, maintaining the integrity of the communication. In the university context, as we are discussing as an example, this method is valuable for ensuring that important messages such as those related to academic policies and administrative decisions are both secure and trustworthy. This approach enhances the reliability and security of digital communications within the institution. Now, the number of keys needed for different group sizes. The group size is 2, symmetric keys are needed 2, asymmetric is 4. 3, 3, and it goes 6. 5, 10, it remains 10. 10, 45, and it goes to the asymmetric goes 20. 100 group size has 4,950 symmetric keys and only 200 asymmetric keys needed. So you can see the clear difference between if you go 100,000, the number is huge, whereas asymmetric keys is 200,000 only. Business requirements for cryptography. So now let's look into this with an example. This diagram highlights several key aspects of ensuring software and data integrity within the university system. This involves implementing measures to protect software applications and data from unauthorized access, or alteration. By using techniques such as encryption, digital signatures, and secure coding practices, universities can maintain the integrity of their software and data. This ensures that academic records, research data, and administrative information remains accurate and trustworthy, which is crucial for institutions' operations and reputation. Another critical aspect is ensuring secure collaboration between entities inside and outside the university. In an academic setting, collaboration often involves sharing research findings, co authoring papers, or working on joint projects with external partners. Secure collaboration tools and protocols such as encrypted communication channels and access controls are essential to protect sensitive information during these interactions. This helps maintain the confidentiality and integrity of shared data, fostering that among collaborators. Ensuring secure cloud computing is also vital in a university environment. With the increasing use of cloud services for data storage, application hosting, and collaborative platforms, it's important to implement robust security measures. This includes using encryption for data at rest and in transit, implementing strong authentication methods, and regularly monitoring cloud environments for potential threats. By securing cloud computing, universities can protect their digital assets and ensure the continuity of their operations. Lastly, in this specific example case, providing secure transactions with consumers such as students and faculty is essential. This involves safeguarding personal and financial information during transactions like tuition payments, registration process, and accessing online resources. Implementing secure payments gateway, using encryption for data transmission, and adhering to data protection regulations are key steps in ensuring secure transactions. This not only protects individual information but also builds trust in the university's digital services. So best practices for PKI user within the enterprise and organizations. What are the business drivers for using within the organization? I suggest you to look at this slide very carefully and conduct research using the IEEE Explorer or Google Scholar to answer all these questions, and this will be a good learning for you to figure out on your own how to find the research that has already been published by other authors and published researchers, academicians, professors, and students who have worked on the PKI in earlier. So I would suggest you to look into this very carefully and conduct a little bit of research for your own learning. The digital certificates and key management. The digital certificates used by individuals and servers to provide unknown third parties with a known secure copy of their public encryption key. Certificate authority issues digital certificates after verifying the identity of the end user. Registration authority, as mentioned earlier, verifies the identity of an individual, initiates the certification process with the CA or the certificate authority on behalf of the user, and perform certificate lifecycle management. Digital certificate looks like this. The domain validated or DV is a certificate confirm that the certification was issued to someone controlling the domain name system or DNS. Domain included in the certificate. These are the certificate validation levels. Organizational validation or OV, a certificate go deeper and verify the identity of the business named on the certificate. Extended validation or EV certificates provide the strongest degree of trust, verifying the physical presence of the certificate subject. Digital certificate and key management happens from the generation to distribution to storage, with the usage, recovery, termination, and archival. These are the components of the key management, and I suggest you to look into these at Google Scholar and IEEE Explorer to learn more so you understand how the dynamics work in the digital certificate domain. The key management considerations: key should be long enough to provide the necessary level of protection. Keys should be random and algorithm should use the full key space. Key's lifetime should correspond with the sensitivity of the data. The more a key is used, the shorter its lifetime should be. Asymmetric cryptography requires a longer key length than symmetric cryptography to achieve the same level of security. Diffie-Hellman key exchange enables two systems to receive symmetric keys without a previous communication, provides a key distribution, does not provide encryption or digital capabilities. RSA symmetric encryption algorithm developed to prevent man-in-the-middle attacks. MITM. Most popular public key algorithms can be used for digital signatures, key change, encrypt, and decryption. Elliptic curve cryptosystem or ECC provides the same functionality as RSA, more efficient than RSA. The attributes are keys, key length required, example algorithms, key exchange, encryption needs, and security service provided. So I suggest you to look into these asymmetric algorithm and symmetric algorithms to conduct a little research on your own. So this will allow you to understand how algorithms help in both asymmetric and symmetric domain. Certificate authority, a trusted organization that maintains issues and distributes digital certificates. CAs may be internal or provided by the third party. Certificate revocation list or CRL, a list of invalid certificates. Online certificate status protocol or OCSP, a method for live interactive verification of a certificate status. The certificate practice statement or CPS provides details on the business process used by the CA to verify the identity of certificate owners. That's a certificate authority looks like as a trusted certificate authorities when the certificates are issued, and the expiration and keychain are also given. Now let's look into this with a detailed example. Let's break down this into a story. In a bustling digital world of a university, Alice needed to securely communicate with her colleague Bob. To ensure their conversation remains private and authentic, Alice turned the university's public key infrastructure or PKI system. She began by making a request to the registration authority, a trusted entity within the university's network, to obtain a digital certificate that would vouch for her identity. The RA, upon receiving Alice's request, needed more information to verify her identity. Alice promptly provided the necessary details, which the RA then used to request a digital certificate from the certificate authority. The CA, acting as the central authority in the PKI system, was responsible and in responding for creating and managing digital certificates for all university members. With Alice's information verified, the CA crafted the digital certificate specifically for her. This certificate was like a digital passport, confirming Alice's identity within the university's network. The CA securely sent this certificate back to Alice, ensuring that only she could access it. Meanwhile, Bob, who was waiting to communicate with Alice, needed to verify her identity before they could proceed. He requested Alice's digital certificate, which she promptly sent to him. The certificate was Bob's assurance that he has indeed communicating with real Alice and not an imposter. Finally, Bob verified Alice's digital certificate using the university's PKI system. The certificate checked out, confirming Alice's identity and permitting them to proceed with their secure communication. With the PKI system in place, Alice and Bob could exchange information with confidence, knowing their conversation was both private and authentic. Thanks to the robust security measures provided by the university's digital infrastructure, this was possible. Confidentiality, integrity, authentication, and non-repudiation. Confidentiality is ensuring that the only intended recipient can read the message. Integrity is to ensure message received was message sent. Authentication allows someone to prove his or her identity to another. Non-repudiation ensures the third party can verify that a message came from a purported sender. Digital signing. Digitally signing an email allows the receiver to verify the contents were not modified after the data was sent. Digital signatures provide non-repudiation. Digital signatures can be used to identify if the user has signed off or approved a particular document. So now let's look into this with an example. The image illustrates the process of creating digital signature, a crucial component in ensuring the authenticity and integrity of digital documents within a university system. The process begins with the document that needs to be signed digitally. This document is first passed through the cryptographic hash function, which generates a unique hash value, often referred to as a message digest. This hash value is a fixed size string of characters that uniquely represents the original document. Any change in the document would result in a different hash value, making it an effective way to detect tampering. Next, the hash value is encrypted using a signer's private key, creating a digital signature. This encryption process ensures that only a person with the corresponding public key can verify the signature, thereby confirming the signer's identity. The digital signature is then attached to the original document, forming a digitally signed document. This combination of the document and its signature ensures that the document has not been altered since it was signed, and that it was indeed signed by the claimed signer. In a university setting, this digital signature process is invaluable for securing important documents such as transcripts, research papers, and administrative records. By using digital signatures, universities can ensure that these documents remain authentic and unaltered, providing a high level of trust and security. This process not only protects against forgery, but also streamlines the verification process, permitting recipients to easily confirm the legitimacy of the documents they receive. So this is the digital signature verification. That's how it happens in this typical depiction that you just have witnessed. PKI is a strong authentication mechanism, provides integrity, confidentiality, and authentication, and non-repudiation in a single framework. PKI is not an answer to all security questions or concerns, does not provide authorization, does not ensure that the end user can be trusted. If PKI key management is mishandled, entire PKI system could fail. Managing a secure environment with multiple keys and multiple entities can be overwhelming. Properly maintaining a PKI comes with a financial burden. Encrypting, so implementation of business cryptography, encrypting hard drives as a preventive measures in case of laptop or other mobile devices stolen. Encrypting removable devices such as universal serial bus, USB drives, encrypting instant messaging communication, encrypting file transfer within and outside of the network, encrypting highly sensitive data, encrypting information and mobile devices, specifically on mobile devices. Distribution of keys within an organization is a vital part of key management Organizations must ensure that keys are safe and distributed securely. Some organizations may choose to outsource these services. Outsourcing can be expensive if there are many systems, communication paths, or files that need to be encrypted within the organization. In-house key management versus outsourced key management. Total costs associated with IT resources and knowledge. Managing keys in-house requires an organization to manage the services level agreement with various business units. Can an organization trust an outsourced key management provider? That's a good question. What do you think the answer could be? What level of support can outsourced entity provide? This is also a question that I would request you to kindly ponder upon and conduct a little research on. All digital certification implementation are done through a root CA or a certificate authority. A root certificate authority signs every certificate. Subordinate certificate authorities can be established for more specific needs. Now let's look into this with a university system example. This diagram outlines various components involved in managing digital certificates within the university public key system or infrastructure PKI system. At the core of the system is the policy authority, which establishes the rules and guidelines for issuing and managing digital certificates. The certificate manufacturer is responsible for creating the certificates, ensuring they meet the necessary security standards. The certificate issuer then distributes these certificates to the appropriate individuals or entities within the university. Additionally, the revocation manufacturer handles the process of revoking certificates that are no longer valid or have been compromised, ensuring the integrity of the system. Supporting these core functions are registration authority, authorization service, and repository. The registration authority verifies the identity of the individuals or entities requesting certificates, ensuring the only authorized users receive them. The authentication service validates the credentials of users attempting to access the system, providing an additional layer of security. The repository serves as a secure storage facility for the certificates, ensuring that they are protected and readily accessible when needed. In a university setting, these components work together to create a robust and secure environment for digital communications. By implementing a PKI system, universities can protect sensitive information such as students' records and research data from unauthorized access and tampering. This infrastructure not only enhances the security of digital transactions but also builds trust among users, ensuring that communications and data exchanges are both secure and reliable. Communications with suppliers, customers, and business partners should be seamless. Organizations may be geographically dispersed, and it would be more advantageous to have multiple CAs available to these various locations. Organizations do not want to take on the costs associated with managing a CA on site usually. The security placed around individual certificate authorities is assessed, is access granted to any employee, or are there strict constraints around it? What do you think? How does an organization knows that it can trust a person it does not employ? I also suggest you to find the answer for this question. An organization may want to control its own CA because of the higher security requirements, not possible when outsourcing a CA. Organizations with high security requirements more apt to manage the CA locally where they have more control. So let's answer these questions one by one. What databases will be used for PKI? PKI systems typically use secure relational databases like MySQL or PostgreSQL to store certificate information, and may also utilize directory services like LDAP or LDAP for managing users' data. What are the legal and policy considerations for the CA? The certificate authority must comply with the data protection laws and adhere to policies ensuring secure certificate issuance and management, including user authentication and revocation procedures. What are the trust relationships and how are they established? Trust relationships in PKI are established through a chain of trust where each certificate is signed by the trusted CA, creating a hierarchy that allows users to verify the authenticity of certificates. How will PKI be deployed? PKI deployment involves setting up a CA, configuring registration authorities, and implementing secure communication protocols, often integrated with existing IT infrastructure for seamless operation. Who will have access to the systems and how will this access be monitored? Access the PKI systems will be restricted and authorized personnel to the authorized personnel with access monitored through logging and technically logging and audit trails to ensure accountability and detect authorized activities. The case studies and examples. Here are a few case studies. The private sector is Parrot Systems, rollout of PKI and lessons learned. Choose recognized industry leaders as vendors, set clear expectations for management and end users. Make sure PKI can be maintained. Ensure ease of rollout and use supportability and leverageability of resources. Whereas public sector, the United States Patent and Trademark Office, USPTO, implemented PKI to achieve the following: confidentiality for information exchange, integrity of the patent application, authentication, and with whom USPTO is dealing electronically. Critical infrastructure is technically VeriSign, certificates issued to person posing as Microsoft employee. Example shows how the PKI's process failed because of CA issued the certificates without appropriate verification. The PKI components and their roles, we have discussed that in quite detail. Non-repudiation and digital signatures, we also looked at a few examples within the university systems and also the PKI certificate authorities, as we have discussed in quite depth. And we also discussed the encryption services and processes. So hopefully this lecture has given you some decent understanding of PKI and related infrastructure. Happy learning. See you in the next lecture.